You see the famous climate stripes. And this figure implies that we can choose exactly what kind of world we're going to live in depending on climate action. If we do a lot of climate action, we'll end up with 1.3 degrees warming in the year 2200. If we try to do our best to burn as much coal as we can, we'll end up with 8.3 degrees in 2200. And most of us here know that that's not the entire story. There's also the carbon cycle. If we are unlucky, there might be less carbon absorbed by the Earth. And there is climate sensitivity. Depending on physical feedbacks, there might be more warming for a given concentration of greenhouse gas emissions. Concentration. This talk is about the latter, so the climate sensitivity, and I will be talking about estimating climate sensitivity using emergent constraints from historical warmings, and this is work I've done together with Peter Cox and Mark Williamson. The latest generation of models has this group of models over here. I hope you can see my mouse. That has way higher climate sensitivity than the IPCC likely range of 1.5 to 4.5. And these models have been developed by modeling centers that are usually really good, so they can't really be dismissed out of hand. And it's now a very important question to ask whether these are realistic and whether it's necessary to adjust the IPCC range upwards and make more drastic emission cuts to reach Paris, or whether it's even possible to reach Paris at all. So as a reminder, I'm going to talk about two different metrics of climate sensitivity. One is TCR, the transient climate response, which is defined as the climate response after 70 years of 1% increase in CO2 concentrations, and the equilibrium climate sensitivity, which is defined as the warming after the Earth has equilibrated, which typically takes about thousands of years because of the high ocean heat content. And there are multiple reasons why it's really difficult to estimate these metrics of climate sensitivities. For simplicity, I've put them in two different categories: the bottom up. So if you model it with a climate model, the initial warming due to CO2 or other greenhouse gases is quite easy to estimate, but what makes it difficult is the feedbacks that enhance that warming. And specifically difficult are the cloud microphysics, because they happen on a very large scale and the climate models have a broader resolution. Top down, looking at historical data sets is also not really easy. You need to combine the historical temperature rise, which we have a good sense of, ocean heat uptake, and historical radiative forcing. And especially the radiative forcing from aerosol is something that we cannot estimate with a very high degree of accuracy. Combining this data, you can estimate ECS. Let's delve a bit further into those aerosols. Over the last 150 years, we've seen a gradual increase in aerosol forcing, and here in this graph, it's the aerosol optical depth that's plotted, up to about the year 1970s, when there were these clean air laws introduced in quite a few countries around the world. And since then, greenhouse gas emissions have increased quite rapidly, but the aerosol emissions, which have a cooling effect, have not risen as fast or have even decreased a bit over the last couple of years. And this is a fact that we can exploit when trying to estimate climate sensitivity, because this is the reason that it's so difficult to estimate sensitivity from observed warming. Let's look at the models now. On the left hand, you see the last 150 years again, and what the model radiative forcing is in a model imbalance. One of the things that comes clear is that volcanoes are quite annoying and we want to avoid them because they give a very clear dip in radiative forcing. On the right hand, we see an increased radiative forcing over time, and it typically really takes off over here around 1980. On the other hand, the spread in the model of radiative forcing increases early around 1960, and that is again this effect of the aerosols, which are quite differently incorporated in different models because we don't know exactly what they do. The signal to noise ratio between the two doesn't really cross the one line till 1970. And then after that year, you consistently see a signal to noise ratio higher than 1. So again, that is what we're going to exploit in our emergent constraints. The climate models, if you look at that temperature, can be grouped into the most sensitive, lower sensitive, and the least sensitive models. And you can see that within this group of most and highly sensitive models, there are roughly 2 groups again. One which displays way too much warming over the historical period. The black lines are the observations. And another one which portrays extreme cooling when the aerosols start to turn on. And then again, a very rapid rate, more rapid in the observations. The low climate sensitivity, the least sensitive models display not enough warming compared to the observations. And you've got this middle group, which for some models is quite accurate compared to observations. So we're going to the emergent constraint now. The methods, we took the historical warming since 1975. We took a mean of 4 global data sets. For each model, we computed ECS using the Gregory method and also TCR using a standard method. We extended the models to 2019 using RCP 8.5 for the CMIP5 models and SSP 4.5 for the CMIP6 models. Quite a few of you might know that the RCP 8.5 is a very unrealistic scenario if you look further into the future. But if you compare it to what we've actually seen in terms of emissions and concentration, then that is the most realistic scenario to extend models to 2019. We combine this information in emergent constraints of historical warming versus TCR and ECS. And the functional form of this emergent constraint is determined from energy balance models. Yesterday, we already saw that sometimes it goes extremely wrong when you assume there is a linear relationship when in fact there isn't. And we will see that again with the emergent constraint on ECS. So starting with DCR, some mathematics. We follow this paper by Jimenez La Cuesta using a 2-box model with 2 layers, radiative forcing, feedback, ocean heat uptake with an ocean efficacy term, which sort of makes your feedback time dependent. And using 2 assumptions, no change in deep ocean temperature and the upper ocean being in equilibrium, you can derive a very easy equation for TCR being linearly related to temperature. These 2 assumptions are reasonable on timescales longer than a decade when your upper ocean is in steady state and shorter than a century when your deep ocean hasn't heated much. This then is the emergent constraint. You can see that CMIP5 and CMIP6 are very comparable. The lines overlap for most of the area. The uncertainty and observation is not only sort of the uncertainty of these observational data sets I talked about before, but also includes the internal variability, which we estimate from the model internal variability. Oh, I skipped one. And these are the probability density functions. If you compare that to the AR5 likely range, which is based on a lot of different forms of evidence, now you can see that the emergent constraint is way tied to the confidence interval is way smaller. The reason that the CMIP6 interval is wider than the CMIP5 one is mostly due to internal variability, which we estimate per generation as the mean of the internal variability of that generation. And the TCR, the median TCR for CMIP6 is 1.68 with a 90% interval of 1 to 2.3. Let's look what happens if we take some of these assumptions and vary them a bit. If we take an earlier end date, so use less data, the uncertainty increases and the value of TCR increases a bit. Smoothing doesn't matter much. Taking a different end year doesn't matter, a start year doesn't matter much either, except at the end where you lose basically all of your information. You only look at the last couple of years. Another question that sometimes appears in the literature is what type of regression to take. We used ordinary least squares, where we took either just one initial value member, or we took the mean of different initial value members. We also developed a hierarchical Bayesian method to include that information, extra information from these initial value members. And what we see in average is if you only take one value per model, you slightly overestimate your certainty, but it doesn't matter much. As a comparison, I've also included orthogonal distance regression. The implementation will probably give a slight bias to the left, so I wouldn't read too much into that, into the fact that this is slightly different from the other three methods. A further discussion within this in the literature is how much does it matter which models you include and exclude. The default constraint here, I've included all the models I could get my hands on, but it is also a fair assumption to only include one model per modeling center, because a lot of the time these modeling centers have very related climate sensitivities and other implementations in their model. So you have duplicate data points, which might bias your regression, but in this case, it did not matter much. Then on to ECS. We know there's no linear relationship between TCR and ECS. The ratio increases with climate sensitivity. And that means that for moderate values of TCR, you sometimes end up with quite high values of ECS. And it's probably a bit more difficult to find an emerging constraint on ECS, especially if ECS were to be high. So let's do some mathematics again. Again, we use the two-layer model. We use the definition of ECS and the same assumptions as before, which means that the upper ocean is in steady state and the deep ocean doesn't warm. Means that you get these approximate equations. It's two equations, so you can eliminate both gamma and lambda from the definition of ECS. And you can write ECS as a function of observed temperature. And there's two parameters in that equation. The S parameter is a fraction of the radiative forcing to doubling. So it's typically about 0.6, I think. And the E is the ocean heat uptake parameter. These two parameters aren't identifiable. As you can see, if you plot your function of delta T to ECS as a function of this forcing parameter, it gives a nonlinear shape. And if you do that with your your ocean parameter, you get a similar shape. It's really important to have that functional form correct, because if you don't have it correct, your slope of your function will probably be off, which means that your uncertainty estimates will be off, and that can be easily off by 50% or something. So what we did is we looked at an analytical solution where you don't have these assumption of no deep ocean heating and your upper ocean being a steady state. And we could only find an implicit solution here using the analytical things. So we had to do some numerical computations. And what you see is that the functional form using this implicit solution without these assumptions is basically the same with some different parameters, with some parameter changes as the one with these assumptions. So that gives confidence that we found the right solution to this two-box model. Then the constraint itself. Again, we're comparing CMIP 5 and CMIP 6. The constraint on CMIP 6 is stronger. The models fall better into this line. The spread in CMIP 5 is a bit larger. And the median estimate is 2.6 with a 90% interval between 1.5 and 4 degrees Kelvin. So the conclusions. It's very unlikely that ECS is higher than 4.5 and TCR higher than 2.5. And I don't see any reason to, based on this work, to change the IPCC recommendations or the IPCC estimate. ECS might be further restricted if you do include estimates of ocean heat uptake, and I've seen some papers over the last couple of months that actually do that. And the third one is that I think there is an emerging consensus on the values of ECS. There's quite a few papers that have come out over the last couple of years that all indicate that ECS is around 3, which we knew before. But this is in contrast what we had 8 years ago, where there was a divergence of, depending on what type of method used, you could have different estimates for ECS. The same is true for TCR, where estimates are converging around these middle estimates that we already had before. Okay, that was the end.